a cylinder, but that would go through the origin, wouldn't it? Wouldn't that be right up through the center? I don't want it there. Where do I want the center of that thing to be? The center of it should be at 1, 0, shouldn't it? So look, if I'm looking straight down on this, let's say this is my x-axis, this is my y-axis. Here's the sphere, right? Radius 3. My drill bit comes in here like this, right? Comes in like that, drills out. So the center of my cylinder should go through this point 1, 0. Very good. All you do, remember how we shift things around, right? X minus h squared plus y minus k squared. The h and the k move your center. So this is going to move it to 1, center to 1. Okay? Well, I've done what was requested. It was requested that we find the equations of each one. Now, find the what? The range. How do you mean range? You mean like the polar stuff, like r and theta and all that? I'm okay with that. But I would still like to hear, like, what's the method, like what are we going to do? Like what are we finding the volume of? What do you want to find the volume of here? So you're trying to go about this problem by actually finding the volume of what we took out? Yes? Do you know the volume of the sphere if we never took anything out? Yes, right? Yep, go ahead.
Find the volume of the cylinder and subtract it from the sphere.
I agree, kind of. Okay, yes, we all can find the volume of a sphere, right? There's no calculus involved in that. We just look up a formula for it and we're done, right? If we know the radius, we know the volume. So we take that answer and we subtract from it the volume of the cylinder, kind of. Because the problem is that, what's the problem?
The cylinder goes on.
Yeah, see, the cylinder keeps going up. So where do you cut it off? At the top, right? What's the top look like, though? Let me see. I thought I had done this where you could see it. Doesn't look like I did. Oh, here we go. That's what I wanted to do. If I take this all out, yeah, it's hard to see that. I'm going to try and zoom in on this. I hope this works. If I rotate this, yeah, that's going to work. You see, that top edge of the cylinder is part of the sphere, isn't it? You have to account for that. So let me go back and ask you a question. Do you have a top cap and a bottom cap? Yes? Right? The top cap of this part that we drill out is the sphere. What's the bottom cap? The sphere on the other side, right? Now I could make my problem a little easier by, instead of going on the sphere to the other side, I could just use the xy plane as the bottom and then find that volume and double it. You don't want to do that? I like that idea. Okay, so the top part's going to be the sphere. The bottom part's going to be the xy plane, which is z equals 0. And the only thing left is what's the region of integration. So let me kind of write what I've said down here. I'm going to go with the approach. My approach is going to be that we have a top function f of xy, which is the sphere, but I have to solve it for z, don't I? Oh, we love seeing x squared minus y squared, don't we? And then the bottom function, which is going to close off the bottom of the solid, we all agreed would be 0, right? And now the region of integration. Isn't the region of integration that circle? The trouble we have right now is putting that into polar coordinates, because I'd love for this problem to be in polar coordinates. Is that a rectangular polar, is that a polar rectangle? Is your angle between two constants and your radius between two constants? So if I look at this angle, if I rotate, let's say to here, is my radius between two constants? Imagine a dotted line right there. So I'm allowed to walk from here to here, right? If I rotate a little bit more to here, is that radius still the same? It's not, right? If I rotate this much, I'm allowed to walk out that far, but if I rotate further, I can't go as far, can I? And if I rotate even more, it's even shorter. Agreed? Somehow, how far I walk out is a function of how far I rotate. And this is what I was just getting at a second ago with that picture that we had, where I said we had h1 of theta, h2 of theta, right? Your angle's allowed to change, but how far you walk out changes when your angle changes. That tells me it is not a polar rectangle. So how in the hell do we get the restrictions that we need? We still need some restrictions on theta, and we need some restrictions on r in order for us to convert to polar, right? So we sit here and we look at it and we think about it, and then we realize, wait a minute, hold on. What do we know about that circle? What I know about that circle is that it follows this equation, right? That's the equation of that circle. In two-dimensional space, that's a circle. In three-dimensional, it's the cylinder. But do you agree? Now, I'm just going to mess with this for a second. I'm going to expand this out, right? Anybody see anything in there? Think polar. Think polar. X squared plus y squared is r squared minus 2, what's x in polar? R cosine theta. Got that? And then 1 and 1 on both sides, subtract 1, and you get equals 0. Now remember what we're trying to do. We're trying to find restrictions on r and theta. Theta should be stuck between two constants, but my radius should be stuck between two functions of theta. Can you solve this equation for r? It's a quadratic in r, isn't it? What can you factor out of each of these? R. So if I have to factor out an r, I get r, and then r minus 2 cosine theta equals 0. Set each one of these equal to 0. What do you get? R is 0, and r minus 2 cosine theta is 0, which means that r is equal to 2 cosine theta. So in order to draw this circle in polar coordinates, you need r to be 0 or r to be 2 cosine theta. Now think about r being 0. If r is 0, does that draw this circle? No, if the radius is 0, where are you? Right there, this point right here. Okay? That point is taken care of by that equation right there. Then this should draw the rest of the circle. Let's see if it does. Are y'all with me? Let's see. Let's let theta, just for example, let's let theta, I'm going to do a good old-fashioned t-table. Theta r. If theta is 0, what's cosine of 0? 1. 2 times 1? 2. So if my angle is 0, then I should walk out 2. So if my angle is 0, I should walk out 2 and draw a dot. If my angle is pi over 4, how far do I walk out? Well, cosine of pi over 4 is root 2 over 2 times 2. It's just root 2. Root 2 is about 1.414, something like that. So 1.414 is about this far, right? But I'm supposed to walk out that far when I'm aimed at pi over 4. Pi over 4 is 45 degrees. Wow, that's right there. Do y'all see that? What would happen, and this is kind of an absurd case, but what happens if my angle is pi over 2? So I'm aiming straight up and I'm saying, okay, how far do I walk out? Cosine of pi over 2 is 0, so it says don't go anywhere. So guess where you are? Right here. Got it? So far, I can draw the top half of this circle by letting my theta go between 0 and pi over 2. Understand? How do you think we're going to get the bottom half?
Negative.
Go negative. So if you go down and you start letting theta go negative values all the way to negative pi over 2, you'll draw the bottom half. So do y'all kind of get this? My restriction on theta is going to be between where and where? Negative pi over 2 and pi over 2. And then my restriction on r, how far I walk out, always has to be between 0 and 2 cosine theta. This is h1 of theta. This is h2 of theta. Now this is a true function of theta, isn't it? Theta actually makes a difference here. This one doesn't make a difference. 0. Questions? This is what we were looking for, right? This is what we were hoping for, is something that would draw this region. And I believe we've got it. All right, now double integral time. What we were going to do is we were going to find the volume of the part that was drilled out. And so we decided to take a look at the top cap being the sphere and the bottom being the xy plane and then doubling the answer, right? So the part that we're drilling out, and I'm going to make sure I'm clear on this, the volume of drilled out part of the solid is 2, I'm going to erase this, is 2 times the double integral, I'm going to polar, r d theta. That has to be this order because theta is between 2 constants. They were negative pi over 2 and pi over 2. My radius was stuck between 0 and 2 cosine theta. And then it was just the f function minus the g function. Here's the f function. But to polar, what is that in polar? Root 9 minus r squared, right? Minus 0, so it doesn't matter. And that's it right there. And then you would go and integrate that. But I'm not going to say dot, dot, dot here. This we could not do by hand. The first integration is easy. The first integration is a basic u sub. But the second integration, I believe you would wind up getting something like you're trying to integrate, forget about constants, but I believe it's something like square root of like 9 minus 4 cosine squared, if I remember correctly, something like that, d theta. Something like that. You're trying to integrate that. And that ain't happening. So. That's why I changed the problem on the take-home. Questions? Your problem that is on your take-home exam is very similar to this problem. In fact, I probably gave you way too much here. But your surface on top and bottom is a little different, and it makes the integration possible. It's going to be a little messy with the integration, but all within, fair game stuff. All right, so what would we do now to find the final answer? If we were able to find this volume, right? We got it. We double it here already, right? Find that answer. We take that answer and subtract it from the volume of a sphere, which you have to go figure out. The difference on your take-home problem is since it's not a sphere, right? You don't have a formula for it, and therefore you have two problems that you have to do here. You have to find the volume of the paraboloid first, which is a double integral. Then you come and take this away. Do you understand how that's two different problems? Okay. Enjoy. All right, that's it for that section. We are going to very briefly talk about 12.4. And when I say brief, I mean we're going to be done here in 20 minutes, I think. So some of the applications. We can get really, really heavy into applications in this class, or we can actually finish the book. And I choose to finish the book as opposed to do heavy applications, only because everything we've done so far is enough for you to do this. It's just a matter of making the connections between, a physics class and a double integral in there, and then doing the double integral, which is what we're trying to show you here. But here are some of the things you can do with double integrals. Suppose you have a lamina. A lamina is like a two-dimensional sheet, a piece of paper. That's a lamina. All right? And it has some weird shape to it. Here it is. And then the density at every point, right? Remember, density is mass divided by area in this case, because it's two-dimensional. So you're looking at, what you're trying to do is you're trying to figure out what the density is at each point, and then you can ask questions like, well, what's the mass of this thing? Okay, what is its mass? So what we deal with in terms of laminas are what are called homogeneous laminas, which are laminas like a sheet of paper, where we assume basically the density is always the same. If you cut out a 1 inch by 1 inch square from anywhere here, take two of them, two 1 inch by 1 inch squares, and weigh them, they should weigh about the same, right? Because we're assuming the density of the paper is the same throughout, uniform, homogeneous. And then you have laminas that are non-homogeneous, which would be something where the density varies throughout the lamina. And that's what we're interested in. What if you have a more complicated lamina where as you look through it, its density changes? So suppose the density is variable, all right? Then the total mass of the lamina is the sum of the mass at infinitely many infinitesimal rectangles. So you're basically cutting up this lamina into a bunch of little tiny rectangles, and you're finding the mass at each one. And if density, if you know the density at every point, so that has to be given to you, the density at every point, density being mass over area means that you can solve this for mass, and mass would be equal to density times area. Density you're given is a function. Here's your density function. So density you're given, area we know, because that's what we've been doing. So you're adding up all these little masses, which means you add up the density times the area. And replace that with F, and that's what we've been doing, right? So all that's changing here is that we have the function actually means something now. F of xy, if it represents a density function of a lamina, then doing that double integral over that region gives you the mass of the object, mass of the lamina. If instead we like to do something that involves electromagnetism, something like that, we could look at a lamina again, a flat sheet of paper, and we could say, hey, look, check out this sheet, whatever it is. It has a charge at each point. Some charge density is what they call it. Then if you look at and you're trying to find the total charge on this lamina, then what you do is you multiply the charge density times the area, and you get the charge at each little infinitesimal, and you add those up, you get the total charge. So again, it's the same concept. What is the meaning of this function? In the previous example, rho of xy was a density function. In the second example, it was the charge density. So if you do this double integral, it gives you the total charge. Again, all I'm trying to do is trying to get you to see that in a physics class, if we give that function f, which is what we do in this class, f, if we give that some meaning, then we can correspond it to either like total charge or total mass. And there's no restriction. It doesn't have to be just those two functions, but those are common ones. So a lamina is formed by the region bounded by these curves. The density is given by this density function. Find the total mass. So this one's going to go fast. I have a lamina 1 minus x is that. Y equals 1, x equals 1. So y equals 1 looks like this. X equals 1 looks like this. Everybody see the region bounded by those three? Okay. The density at a point in that lamina is x times y. So if I come out here and I say, I don't know, I pick the point 3/4, 3/4. That point lives in there, doesn't it? What's the density at that point? What's the density of the lamina at that point? It's the x times the y, right? X times y. So it's 9/16, whatever they're measuring it in, right? But if I change and I move this to 1/2 and go up 3/4, then now it's changed, right? Now it's 3/8, different density. So this lamina, its density changes throughout the shape, throughout the figure, and we're trying to find its total mass. So all it would be is what? Let's see how many of you got this down. See a lot of glazed staring into nowhere. So how do you want to do this? Do you want to go polar? Every time I say, do you want to go polar, I always think of, do you want to go postal? You've heard that before? Postal, like go crazy? Isn't that a term that they use for that? Go nuts? How do you want to do this? Type 1? Type 1 region? Okay, I agree. We're integrating. What are we integrating? What's our function? XY. Since it's type 1, my x's are bounded between two constants. What are they? 0, 1, right? 0 to 1. My y's are bounded between two functions of x. This one's the bottom one. This one's the top one. So the bottom one is 1 minus x. The top one is 1. D y dx. If you can compute that, you've got the mass of the lamina. All right? I'm not going to. Questions? This is the same exact problem. Everything's the same, except instead of using a density function, using a charge density. So the only difference is the answer means something different, right? If you find this integral, that answer would represent the total charge on that lamina. Now, along with being able to find the mass of a lamina, you can find what's called its moment. Now, this is a physics concept. And we use the moment to compute something else. So first, let's talk about what the moment is. Same lamina, right? There it is, blah, blah, blah. It's got a variable density. So we still have the charge density, the density function right here. You see it? But we've added one thing to it. You see the y right there? Y times the density function. If we compute this, it's called the moment of the lamina about the x-axis. And we use capital M subscript x to represent the moment of that lamina around the x-axis, or about the x-axis. If we switch it, and instead of multiplying by y, we multiply by x, we call that the moment of the lamina about the y-axis. So physics again, moments are basically the mass of the particle times the distance to an axis. Now, why is that useful, computing the moment of a lamina? Well, the next formula. If you have a lamina, same thing, has a variable density. These are all in your book, by the way, and they're all in your notes too. Then one of the most interesting things to find, in terms of a lamina, is its center of mass. Especially if the lamina does not have the same density throughout. Like if you have a flat sheet of paper like this, a rectangle, and it's homogeneous, which means the density is always the same, the center of mass is pretty obvious, right? It's just the center of this. But if this is no longer homogeneous, then the center of mass could be just about anywhere, right? And there are even some objects where the center of mass isn't even on the object. A boomerang is an example of an object that has a center of mass outside of its space. And another one you could take is like just a disk like this. Its center of mass is there, right? Even if it's homogeneous. So finding the center of mass is computed. The center of mass is a point. It has an x and a y coordinate. We call it x bar, y bar. And look at what you do to compute the x and y coordinates. To compute the x coordinate, you have to take the moment and divide it by its mass. To find the x coordinate of the center of mass, you take the moment about the y-axis and you divide it by the mass. Remember, this was the moment, right? I know everyone's tired, but don't help them out. All right, thank you. All right, that was the moment formula, and then we just 1 over mass means divide by mass. But what was mass? Yeah, but wasn't the mass a different double integral? So in order to find the x-coordinate of a lamina, center of mass, you have to do 2 double integrals. One double integral gives you the moment, and you divide it by another double integral, which gives you its mass. And then to find the y-coordinate, it's the other moment divided by the mass. So if you're given a problem where you're asked to find the center of mass of a non-homogeneous lamina, you have to compute 3 double integrals. You have to find the mass, because you need it for both of these, and you need to find both the moments. Here's an example where you're asked to find the center of mass of a region bounded by some things, and then I give you the density function here. What I wanted to do with this was to just show you, like, this is the lamina. It has a variable density. So can you see that the darker shades represent where it's more dense, and the lighter shades where it's less dense? How dense it is depends on the x value. For this particular density function, the x value dictates how dense you are. So the bigger x is, right, the bigger your density is. And I actually did this three-dimensionally so you could actually pop it out of here. And whoa, whoa. You could kind of get an idea of how much more dense that object is out here towards this edge with the height. Now, it's not three-dimensional, but it just gives you some idea of how much of this object's density is over here. So its center of mass should be way over here somewhere, shouldn't it? It's not going to be right in the middle. It should definitely not be, right? Center of mass should not be like right there. It should be this way. So to do it, I only have 2 minutes, 3 minutes, 4 minutes. This was y equals negative 2x plus 6, and this is y equals x. So that's, if you were to draw this region out, that's what you would get. And so you would need your limits of integration. This would be a good type 1 region. So you should go double integral. Let's do the mass first. Mass would be double integral where to where? Well, you have to figure out what's your bound on x. 0 to wherever they hit each other. So you set those two equal to each other, okay? It's 2, all right? I think it's 2. 2 in here, 2, yeah. So if you plug in 2, you should get. And then what's the lower and upper bounds here? Y equals x on the bottom and negative 2x plus 6. Now for mass, what am I integrating? Just the density function, x squared. dy dx. You figure out what this is and you get a number, right? That's your mass. Put it to the side, you'll need it later. Then you come in here and you do the moment, right? So if I want x bar, it's the moment about y over mass, which is 1 over mass times the double integral of what? What changes? These are opposite. I'll go back to the moments. So look, moment, a moment about the y-axis, you use x in here. A moment about the x-axis, you use y. That was it. So it would be x times that, so x cubed. dy dx. What about the limits? Exactly the same. So you're doing almost the same integration, right? Except you're doing x cubed instead of x squared. And then when you do y bar, it's moment about the x-axis over mass, which is 1 over mass, double integral